Welcome everyone to the course of Fundamental of Econometrics for Management Sciences students. This is week 12 and today is lecture number 2 of week 12. As you may already recall that week 12 was focused on the remedial measures for heteroscedasticity. The first lecture of week 12 was mainly focused on the theoretical aspect of remedial measures for heteroscedasticity. We already discussed very extensively the theory and the methods associated with the remedial measures for heteroscedasticity. Today we are going to be more focused on the application side of using the software Eviews and fixing the problem of heteroscedasticity. So before going and linking our learning with the previous lecture to the point where we left it last time, I would like to give you a very quick overview of the remedial measures of the heteroscedasticity. So we were discussing that the remedial measures for heteroscedasticity could be grouped into two. The first group is the case when we have heteroscedastic variance known, then we use the weighted least square method, and the second case is the heteroscedastic variance unknown. In that case, we use a number of educated guesses through which we try to transform our heteroscedastic variance to homoscedastic variance. So in the weighted least square case, when we have the known heteroscedastic variance, all we do is to divide our data, all observations with the respective heteroscedastic variance, and that division transform the original data to a homoscedastic observations. Then we can apply the standard OLS procedure and thus ensure to obtain the blue or best linear unbiased estimator. However, the problem is that the heteroscedastic variance is hardly known. So this method in principle may sound great, but it doesn't work good because we can't apply it having no variance being available. So the second methods are under the heading of the case when we don't know the variance. In that case, we need to have some idea about the variance so that we can use that idea, or we can use that guess for transforming our data. So we can do number of guesses, and on trial and error basis we can transform our data to a homoscedastic variance data. So the transformations which we discussed last time was that we may start with expecting that our true error variance being proportional to one of the regressor or the square of the regressors. So in this case, we can use the regressor values or its square value for transforming the original data to the homoscedastic variance data, or we can use the predicted value of the dependent variable for the transformation. We can also try with log of dependent variable or using double log model instead of the original model in order to ensure that our data become homoscedastic. Discuss that we can try a procedure or we can use a trial and error by applying one of these fixture and then checking if the heteroscedasticity problem has been removed, and if it still persists, we can try one of the other from the list, and we continue that until we solve the problem of heteroscedasticity. So in our previous lecture, the last topic was that I asked you to use the remedial measure of heteroscedasticity that is based on the dependent variable forecasted value. So all I asked you was to run a model of the data in which mileage per gallon was regressed on the top speed, on the horsepower, and on the vehicle weight. Variable forecasted value is proportional to the variance, the heteroscedastic variance. So use that for transformation of the observation and then check if the data is homoscedastic. So the task was named as 12.2 and you were asked to follow the following steps. You were asked first to run the model, then you were asked to generate the 5 transformed variable which were generated by dividing the original variables with with the forecasted value of the dependent variable. However, you were also told to create the constant term transformed as well by dividing by taking reciprocal of the forecasted value of the dependent variable, for the reason being explained in detail in the previous class. So then you were asked to run this model to make sure that you do not include this constant term C when you are applying this in Eviews, because the C transform is already in the model. So you were asked to focus on these 3 questions: run the transform model, apply the PPY test for heteroscedasticity, so that once you run the transform model, you become sure that heteroscedasticity is removed, or if there is still heteroscedasticity, so then you try to use some other transformation method and try again if the heteroscedasticity is removed. So I believe that you have performed these. Now I will take you to Eviews and we see how it works.
So this is my Eviews work file, and as you can see, I have the mileage per gallon data, horsepower, top speed, and then the weight. So I have all the relevant variables data available with me, and as I told you, first of all we have to transform this data, and then we have to estimate the transform model. So for the steps which I ask you to perform was, first of all I ask you to regress mileage per gallon on top speed, then the horsepower, and then the weightage of the vehicle. Open them as a equation, take the constant at start so that it gives me the values as per the defined model. Mileage per gallon being regressed on constant on SP, HP, and WT, the 3 explanatory variable. I press OK. I have the result. Dependent variable, all the explanatory variable with constant, standard error, T statistics, and if you recall, we last time applied white test and BP test and some other test. All these tests confirm that this results is affected with the heteroscedasticity. So now we are going to fix, and the fixture we were applying, we are suspecting that the heteroscedastic variance is proportional to the predicted value of the dependent variable MPG. So I have to calculate the predicted or the forecasted value of MPG. For that I told you that you go to proceed, then you go to forecast, then here you apply this as you name this as MPG underscore forecasted, and you uncheck all other boxes. You press OK. So you got a new variable which we call MPG forecasted, and then we said that we divide each of the variable, all the dependent variable and each of the independent variable along with the constant by this MPG forecasted, and this gives us the transformed variable, and then we use this transformed variable to re-estimate this model. So let me do that transformation. So I go to object, I go to generate series. First I will generate y underscore transform, and that should be equal to MPG, the dependent variable, divided by MPG underscore forecasted. So, and then I press OK. So I got y transformed. So this y transformed is equal to MPG divided by MPG forecasted. Similarly, I transformed the constant term. So the constant term was C transform. I named the constant term transformation as C transform. That should be equal to 1 over MPG underscore forecasted. So I divide this with the MPG forecasted as well. Press OK. So I got C transformed. Then I go again to object. I generate a series. This time I call it HP transformed, that should be equal to HP divided by MPG forecasted. Press OK. So I got HP transformed, then I transformed SP. So I go to object, generate series, I call it SP underscore transformed, that should be equal to SP divided by MPG forecasted. So MPG forecasted, so press OK. So that's MPG forecasted as well. Then I go again, now WT is remaining, so I go again to object, generate series. This time I call it WT transform, should be equal to WT divided by MPG underscore forecasted. Press OK. So I got WT transformed as well. So now I transformed all the dependent variable, the constant and the explanatory variables to its transform form by dividing the forecasted value of the dependent variable. So now what I do, I open these as a new group. So I will freeze this output which I obtained earlier. I will keep this just for in case we need. I will close this group. So now I open a new group in which I say y transformed as dependent variable. I'm going to regress it on C transformed. I'm going to regress that on SP transform. I'm going to regress that on HP transformed, and I'm going to regress that on WT transform. I open these all variable as equation. Now be careful here. As a default, y transformed as a default, Eviews will take the C here as well. You don't need C here because you are already using C transformed here. So I will remove this C from this particular equation. Now I have y transformed, C transformed, SP transformed, HP transformed, and WT transformed. So make sure you remove the C because the C is already there. So once I have this, I press OK. So this is the results. Now this is the results. You can see here these results. Let's discuss this in our slide. So I hope you applied the Eviews by yourself. Now let's discuss the results. So this was the original model, MPG, B1, B2, SP, B3, HP, and B4, WT. This was the original data when mileage per gallon would regress on the constant and the three explanatory variables. And this is the data. This is the output when we transformed the original dependent variable by dividing the forecasted value of mileage per gallon. And similarly, the transformed value of the explanatory variable and the constant. So this is the model which I ask you to estimate. Now, as far as this result is concerned, we are okay till this level. We can see that the result of the original and transformed model are comparable in a sense that the coefficient values are, well, it's just different, but not that highly different. And if you see the signs and the magnitude are comparable. It's not exactly the same, but it's comparable. So we says that okay, the results are comparable, but more importantly, we were not interested in this results alone. We were also interested that if the transform model is now homoscedastic or heteroscedastic still. So let me go back to the original data, and now let me go back to the Eviews, and now let's apply the test. So to apply Y test and BP test for heteroscedasticity, let me go to view, then residual diagnostic, then heteroscedasticity, and here I select BP test with all the default. I press OK. So I have the result of the BP test. This is the F statistic value, this is the variable coefficient value, and all detail. I will hold the discussion on that output for a while. I also apply the other test which we call the Y test, and I press OK, and the result of this model is also given here. So these are the results of heteroscedasticity test, Y test. So this is the result of that. Now let me take that to the discussion part. So let me open my presentation. So testing heteroscedasticity, I hope you perform the white test and the BP test, and the results of these two models are given here. As we know that BP test follow F statistics as here. If you see here, F statistic value is 2.754 with probability value of with degree of freedom of 3 and 77. It's 0.0481. So what does it indicate? It indicates that the F statistic value is statistically significant at 1%, and around 5% is also statistically significant. And if you recall, BP test H0 was, I hope you remember it. In case you forgot, I will just give you a refresher. H0 says that the variances are what? Homoscedastic against H1, that these are heteroscedastic. So when F statistic is statistically significant, it shows that the H0 is rejected and you go for H1, which says there is a problem of heteroscedasticity. And if we apply white test, you see here white test is also statistically significant at 1%. N into R, that follows chi-square distribution, and that shows a very high statistical significance. So this also shows that the heteroscedasticity problem is there. It also have the same hypothesis, H0, the coefficient, the variance is homoscedastic against the variance is heteroscedastic or not homoscedastic. So this also shows that we reject H0 in favor of H1, and we say that the problem of heteroscedasticity is there. So quickly the summary, the result of both tests were shown here, and as we can see that in both cases H0 is rejected, which says that the variants are homoscedastic against alternative hypothesis that these are heteroscedastic variants. So the conclusion is that although we apply one of the transformational method, the problem of heteroscedasticity is still there. The problem is not solved. So you may raise the question, what should we do? Obviously, we have to think of something else. My initial guess of transforming the data using the predicted value of the dependent variable didn't work. So I have to think of solving the problem of heteroscedasticity to use one of the other methods which were available with me. So let's move further and let's apply one of the other methods. So I will call it practical task number 12.3. So now we try another one method. So this time we apply the remedial measure using the log of dependent variable. So instead of using the forecasted value of the dependent variable, we use log of dependent variable. So this task is slightly simple compared to the previous task. We use log of the dependent variable in this method, and we use this log of dependent variable in transformation because the previous method of using predicted value of dependent variable did not work. So we use log of dependent variable, we transform our dependent variable, and then we use this procedure on the next slide, and we see if this procedure works. So now what you have to do is you run this model, ln of mileage per gallon being regress on the other explanatory variables. So now this is a slightly different transformation, and it's easy transformation. In this you just use the transformation for the dependent variable. You generate ln of mpg. We know the procedure as well. Just for repetition, you go to object, generate series, you name a new variable ln underscore mpg equal to log of mpg. So that will give you the log of mileage per gallon. a new variable, and then you regress that variable on the explanatory variable in its original form. And again, we raise these three questions. Run the transformed model. The transform model here is using the log of the dependent variable instead of using the original variable. Then you apply BP and Y test for heteroscedasticity, and then you see if the problem of heteroscedasticity is there. Again, I would request pause the video, perform these tasks in Eviews, save your result, and then compare it with the playing the video ahead. So I will go back to my previous slide. I will hold my presentation here. I would request you on your Eviews software and start performing these tasks. Okay, so now I believe you have done it. Let me go to Eviews. Let's switch to Eviews and let me show you how to perform these in Eviews. So I will close the original. Okay, so this was the original data. We already saw that transformation doesn't work. So now I will just delete the transformation. Okay, so this is my Eviews data. Now I'm going to apply the log of the dependent variable method through which I try to solve the problem of heteroscedasticity. So in order to apply that method, first I need to generate log of mileage per gallon, for which I went to the object generate series, and then I define ln of mpg, that's equal to log, and then within bracket I write mpg, so that generate the log of dependent variable. And now I use log of dependent variable, sp, hp and wt, the three explanatory variable. I open them as equation. I take the constant and start, just to be consistent with the model I have written, and then I press OK. So I got the output for regressing log of mileage per gallon on the three explanatory variable in constant. Now we did again a transformation, and we want to see now if this problem, if this transformation solve the problem of heteroscedasticity. So again, I will save this output for discussion at a later stage. I will put it on top of it, and then I go to process. Now I have to check Y test and BP test for heteroscedasticity. So let me go to view, residual diagnostic, heteroscedasticity test. So I select BP test first with all default option, press OK. So this is the output of the BP test. I will take this to Eviews. So I will take this, I will freeze it, will take it to my presentation for discussion. I go again for applying the second test. So I go to residual diagnostic heteroscedasticity test, press OK. We go to white, press OK. This is the output of white test. So white test, this is BP test, and this is the output of the regression model using ln of mpg. So let me switch to my presentation and discuss these outputs. So this was the 12.3 tasks output. This was the original model, mileage per gallon being regressed on the constant and explanatory variable. This is the output of regression of log form being log of dependent variable being regressed on the original model. Now, if we compare the results, both results are shown here. If we compare the result, the sign of the coefficient are same on both the models, but the coefficients of both models are not comparable, and the interpretation of the two is different as well. I have wrote here why, and you should have the answer for that why before I tell you. The reason for difference is that in the left hand side we have dependent variable in linear form and independent variable also in linear form. So here one coefficient, for example, beta 2 shows if SP increase by 1 unit, MP respond by beta 2 unit. But on the right side, when we are using ln of MPG, we have log ln model. In this, beta 2 shows when SP change by 1 unit, beta 2 shows that MPG will respond by beta 2 percentage. So that's a unit change bring percentage change independent variable because it's in a log ln model. In case you forgot that, please go back to the previous lectures. We have a detailed discussions on it. Okay, so that was the output of the regression. Now we believe that this transformations, when was done, it solved the problem of heteroscedasticity. So let me go to the test result. So this is the output of a BP test, and if you see here, we already saw that a BP test is based on F statistics with the 3 and 7 degree of freedom here, and we see here again, if you see here, it's statistically significant, and again it's rejecting H0, and H0 was the variance is homoscedastic. And if we see the white test and its result, it follows chi-square distribution and R-square following chi distribution. It's also showing a statistically significant results, and again H0 is rejected, which says that the variances are homoscedastic. So both tests reject H0, that state that the variances are homoscedastic, against alternative hypothesis H1 that the variance is heteroscedastic. So conclusion is that even after transforming the dependent variable with the into its log form and using that transform dependent variable, the problem of heteroscedasticity is there. So the natural question is, what should we do? As I told you earlier, it's a guess error. It's a guess trial and error procedure. It's time consuming. So now we are going to try one of the other methods on the list and see if that can solve the problem. So let me try another fixture. So in this picture, in this next fixture which I'm going to try is I'm going to use double log model and see if this solution solve the problem of heteroscedasticity. So the method I'm going to use is double log model. You already know what is double log model. Double log model use the log of both the dependent and independent variable in the regression model. So this transformation is used, this double log model is going to be used because the other solutions didn't work. So we are going to run double log model, and we will see again if the problem of heteroscedasticity is prevail or if it's solved. If it's solved, we are okay. If it doesn't solve, we have to try with one of the explanatory variable and solve the problem of heteroscedasticity. So the procedure is explained on for the Eviews on next slide. So let me do it. We have to estimate this model log of MPG being regress on log of SP, log of HP, and log of WT. Now this is not that difficult, but it's just a straightforward task again. But you have to have the log of dependent variable and log of independent variables available, and only then you can run this model. So to run this model, we first need to have the new variable being generated. So the one way which we did in the past was that we can generate log of MPG by going to object generate series and then writing log of underscore MPG equal to log of MPG. So that's one way of generating, or I can name it as ln of underscore MPG is equal to log of MPG. It's up to me whichever name I want to give. So the left hand side is my choice, the right hand side should be the way it is written here. Similarly, I can generate log of SP, log of HP, and log of WT, the three explanatory variable in its log form. So that was the procedure. We learned how to generate the log of the variables. That's one way of running the double log model, that I generate these variables and then I run this model. In case you forgot how to do that, you can go to a video on double log dependent double log model. In that video it is shown in 2-3 minutes how you can do that, so that can give you a quick refresher. So one procedure is generate the log variables and then run the model, or we can do directly run the log model in Eviews, and all you have to do is open these variables in group form and then write this equation in equation window. Instead of using mpg, you write log and you enclose mpg within small brackets. Similarly, you write c, then you take the log of sp instead of sp, log of hp instead of hp, and log of wt instead of wt respectively, and then you press OK. It will give you the double log results directly. So you can use either of these procedures. The second procedure is obviously more convenient and easy, and we have never used it in past, so I'm going to apply that in Eviews. So again, we have to answer these three questions. We have to run the transformed model, that's the double log model. We have to apply BP and White test for heteroscedasticity, and we have to check if the heteroscedasticity problem is still there or if it is solved. So again, I would request you, please pause the video, please perform all these tasks in Eviews, and then go ahead and compare the results on the next slide. I will pause my video. I would request you, please take your data and perform these tests in Eviews. Okay, so I believe you have performed your analysis in Eviews. You have the results ready with you. So now I will show you how to do it in Eviews in case you were unable to do that, and then we compare the results. So let me switch to Eviews. So this is my data, and I have to run the double log model using mpg as a dependent variable and hp, sp and wt as independent variable. So one way of doing this is that I go to object, I go to generate series, I generate a variable log of underscore mpg that should be equal to log of mpg. Then I generate a new variable, generate series. I this time generate log of hp, so log underscore hp, that should be equal to log of hp. Then I generate a new variable, I call it log of sp equal to log sp. Then I generate a new variable and I name it as log of sp is done. So now log of wt, and it should be equal to log of wt. So I have the dependent variable in log form and the other three explanatory variables in log form. So I can select dependent variable, the first independent, the second independent, and the third independent. Open it as a group, as equation. I take the constant at start, I run it. So that's one way of doing it. I run double log model. So I will freeze this output for comparison. I will close this as a group. The second way of running this model directly is I take the dependent variable mpg, I take the first independent variable, I take the second independent variable, I take the third independent variable, I open it as the equation, I take c to the start. Now I write log mpg, then I write log sp, then I write log hp, and finally log wt. I press OK. As we can see that the results of the model run by generating log variables separately or directly using log form in the estimate window like I just did it. both gives exactly same results. You can look into the coefficients of respective variables. So this is the second way through which you can run the double log model directly. Now once we have this output, the next step was that we need to check the heteroscedasticity if it's still there in the transformed model. So for that we go to view, and then we go to residual diagnostic, we go to heteroscedasticity tests, then we go for BP test, we click OK with all the default, and we get the result of BP test. So I will freeze this result for a while so that I take it to the my discussion part, to the presentation. Let me apply the other test. So I go again to residual diagnostic. I go to heteroscedasticity test, and I apply this time white test. Now you should be knowing this fact that the white test is for larger sample size. That I think I mentioned it in when I was telling about the white test. But anyhow, there is two options of applying white test. The first one is, you can see here the tick mark, include white cross terms. What does it mean? I will show you in a while. But if I check or uncheck, it affect the results of this test. So for time being, I will uncheck it, and then I will tell you what is the difference. So if I press uncheck, I press OK, it is just including log of square, log of HP square, log of WT square. So if I go back again, I go again, heteroscedastic test, white test, and I this time keep it check, and I press OK. Now compare it here. It's just 3 term here, but if I keep this checked, I press OK. Now there 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 terms. Now when there is a small sample, relatively smaller sample, it will affect your outcome. So that's why this says, because there is a problem of degree of freedom, and obviously it affects the critical value. So that's why we said that the white test is in principle for the larger sample. But anyhow, for time being, I will just take the one without the cross term. It doesn't affect too much, but still. Now, if we see the result, let me take the result of white and BP test to the discussion part. So let me display it. This is the result of the original model and then the double log model. Again, the results are comparable, but the interpretation is not same because it's double log model, so it gives you directly elasticity compared to the unit changes. So we'll not discuss it here. So this is the results of the two tests. If you look here, the white test with F statistic 0.1533 and the heteroscedastic n into r square with chi-square distribution probability 0.4683. What does it indicate? It indicates that now we cannot reject H naught. We cannot reject H naught. Why we cannot reject H naught? Because the probability value is less than is greater than 0.05. So when we cannot reject H naught, it means we cannot reject this hypothesis that our variances are homoscedastic. Or in other words, if we conclude this, we are saying that the use of double log solve the problem of heteroscedasticity in over this particular data. So it means that instead of using the journal model in which we were regressing just mileage per gallon on the explanatory variables, we should use double log model. It will solve the problem of heteroscedasticity for in our data. So that was the fixture or the solution of fixing the problem of heteroscedasticity using remedial measure when the heteroscedastic variance were not known. We tried a number of remedial measures, namely we first tried with using the predicted value of dependent variable as a transformation and then we tried but it didn't work. Then we used the log form of the dependent variable. It didn't work either. Then we tried with the double log model and it solved the problem of heteroscedasticity. Finally, the last remedial measure is white heteroscedasticity corrected standard errors. Now, we already discussed two broad groups of fixing the problem of heteroscedasticity. One was the case when the heteroscedastic variance was known, and the other when the heteroscedastic variance was unknown. We already discussed that. Now this is the third method and the last method that could be used to solve the problem of heteroscedasticity, and this is called white heteroscedasticity corrected standard errors. So what is this procedure? Let me start with a small background. Let me remind you that when there is a problem of heteroscedasticity, the OLS estimators are not best, or their standard error is not minimum. They have no issue with the parameters estimated value because they are unbiased, because they are consistent. So the problem is not with the estimated value but their standard errors. So what we can do, as these variances are not minimum, so what should we do? White proposed a procedure that directly calculate the minimum or corrected variance for the coefficient. So instead of going for transforming the data and ensuring homoscedastic variance, White proposed a procedure that directly gives the variances that are minimum or that are corrected for heteroscedastic problem. So this direct procedure is called White Heteroscedasticity-Corrected Standard Error, and that directly provide the correct standard errors for OLS estimators. Now there is a long mathematics, complex mathematics involved, that how this process ensure the correct standard error, and obviously at this stage we are not going to use that. We should keep in mind that the this procedure is valid for large samples. Now large is a subjective term. We can't say it at this stage that large mean 80 observation or 800, but for sure the larger the sample the better it is. And as I told you, mathematical background at this stage is not required for us, so we will just see how we can apply this method for obtaining the heteroscedasticity corrected standard errors. So I'm going to apply that in Eviews, and I will show you how this procedure works. As far as the theory is concerned, you should know that White method directly provide you the heteroscedastic corrected standard errors without transforming the data, and it's valid for large sample. We don't need its mathematical background. We should know that much of the theory, and we should know how we can apply that in Eviews. So let me show you. Now this is the last task for this particular topic. So let me show you how we can work. This is the method, White Heteroscedastic Corrected Standard Error method for fixing the problem of heteroscedasticity. So again, get the data of heteroscedasticity from your LMS, and then select these are the three variables, explanatory variable and the dependent variable that we are going to use, and we are going to apply the White Heteroscedastic Corrected Standard Error method in the next slide. So how you can do that in Eviews? So I'm going to apply this on the next slide. So let me show you how we can do that in Eviews. First of all, you have to open these three variables, the explanatory variable along with the dependent variable as a group. Then you have to click on procedure, make equation as a standard procedure you used to follow. But this time, once you have the equation written, once you write the equation, before clicking OK, you go to the tab option at the top and select Huber-White method in covariance method box and leave everything else to default and press OK. That will give you the White Heteroscedastic Corrected Standard Error OLS estimators. Let me show you how we do that in Eviews. But again, I would request first you try yourself and then compare the output with the what the video have. So let me show you how we can do that in Eviews. This is my data, dependent variable, the two explanatory variables. So I will first I will select the dependent variable along with the dependent variable MPG, and then the first explanatory variable, the second explanatory variable, and the third explanatory variable. I open them as an equation. I'll take C to the start so that I ensure the specification of the model. Now in normal circumstances, when we press OK, we get the results. So this is the normal procedure. This is the output. I just save it for comparison. This is the original output when I run the dependent variable on all the explanatory variable. And we already know this is a problem of heteroscedasticity, and we also know from the theory that the coefficient have no issue, but the standard error are not minima. So now we apply the white heteroscedastic corrected standard error procedure. So for that I go again to estimate, and now you see you get this window at the start, dependent variable, regress on constant, and the three explanatory variable. So now instead of doing directly OK, I go to option here, then here I select Huber-White method. I press this one, remove. I keep everything. I go to this Huber-White procedure and I press OK, and here you go. You got the result of White heteroscedasticity, consistent standard error, and covariance results. So let me go to the results. So this is the results of the original model, and this is the results of the White heteroscedastic, consistent standard error, and covariance. So the results of both the models are given, as you can see here. Now what you should note that the coefficient values. Look at the left hand side and look at the right hand side. The coefficient for constant 189.9597, it's the same. SPHPWT minus 1.27, 0.390, minus 1.90, minus 1.27, 0.39, minus 1.90 respectively in both models. So the coefficients are same. What is different? The different is standard error. Look at the standard errors on the left side and on the right side. It's different values. Now we would trust the result of the White heteroscedastic consistent standard error and covariance, and you can see that the probability value, the t-statistic values are different in both. Why it's different? Because t-statistics is obtained by dividing coefficient with the respective standard error, and when the standard error change, the t-statistics values change, and when the t-statistic values change, the probability values will be changed, and these are now more trustworthy results. So we are going to trust these results now instead of the original model. So the point to note here is that if the sample size is reasonably large, we should produce White heteroscedasticity-corrected standard error along with usual Euler standard error to get some idea about the presence of heteroscedasticity. So that's the bottom line. To sum it up, this suggests that when you are running a regression model, it's always good to check for heteroscedasticity, and you can do that while you try with White heteroscedasticity corrected standard error. But obviously this holds true when you have a reasonably large sample size. So that was the final method of fixing the heteroscedasticity problem. Now to summarize the entire topics, the last three lectures and including this fourth lecture was on the discussion of violation of homoscedasticity assumption of the classical linear regression model. We did discuss that the heteroscedasticity does not affect the unbiasedness or consistency of the OLS estimators. However, it makes the estimators less efficient, and they are no more biased no more best estimators, and because of that it becomes less reliable, and we we do not trust anymore the results of the OLS estimators. And then we discussed that there are a number of ways through which we can test if there is a problem of heteroscedasticity. And these ways were considering the graphical method and then the formal test, the BP white test, or the other tests as well. And then we discussed the solution process that involve mainly the transformation of the data that can solve the problem of heteroscedasticity. These transformations were of two types. The first one was when the variance was known, so the data was then transformed through that known variance. If it was not known, we used the trial and error procedure with some educated guesses and tried to solve this problem. These educated guesses were of different form. For example, using the predicted value of the dependent variable, or the value of one of the regressor, or the square of the regressor, or the use of log of dependent variable or double log models. We used some of these methods in Eviews as well, and we saw that at the end the problem was solved by one of these methods. There were also a direct method which is called white heteroscedasticity-corrected standard error method, that instead of transforming the data directly provide us a homoscedastic standard errors. However, this procedure is valid only for large samples. So that was the entire discussion. Thank you. I hope you like this lectures on heteroscedasticity. In case you have any question, feel free to write me or post your questions in comment. I would glad to answer that. Meanwhile, please do like our videos, do share it, and do subscribe our channel. See you soon in next video. Thank you.